Welcome to another podcast. In this episode, we're going to be taking a look at our third and final partial fractions video. This is the way that the book will generally introduce partial fractions, and it's a way that you could do any of these problems. However, I think cover-up is easier for most of the examples that we've considered so far. This is an example where you cannot use cover-up to any great degree, and so I want to go ahead and look at it with you. The key point here is, since this is already factored, I'll just go ahead and label what's going on here. The key point to make is that this is a quadratic factor. It's not linear, it's not even repeated linear. It's purely quadratic, meaning that at least in the real numbers, I can't reduce that any further. There's no way to factor it. Now, if I allowed myself to venture over into the complex plane, I could factor it into x plus I, x minus I. And it turns out that you can do cover-up on that. Now, we haven't done anything like that in class. That might be something for a future project or something like that. But that is an example of just sort of the way in which you can use these methods outside of your normal comfort zone. But we're going to deal primarily with the quadratic factor here on this problem, and we're going to look at the way that partial fractions decomposition is generally taught. So let's consider the decomposition first. I'm going to have to save room here because there's quite a bit going on in this problem. But if I take the 6 over x minus 2, x squared plus 1, then given our familiarity with how these decompositions work, you shouldn't have much of a problem with me writing a over x minus 2 plus, and then I've got the quadratic factor here, which needs a general linear top, and so the numerator is bx plus c. So, like I said, we shouldn't have too much problem with that being our decomposition in this case. Now, in order to work with this, I have to get a common denominator. So I'm going to recombine. Let me just write it out to the side. My goal here is to recombine the right-hand side. In doing so, I obtain a common denominator, multiplying each piece by the part that is missing down below, and keeping things nice and factored here. I don't want to try to string everything out just yet. And then the bottom returns to, or the numerator return, or excuse me, the denominator returns to the same denominator that we started with. So if you're comparing these two fractions, the one we started with and then this new decomposition, a couple of things stand out. The denominators are exactly the same, which means that since these two things are equal to each other, the numerators must also be the same. Basically what I'm saying here is I need to take this numerator and write it out and then set it equal to the numerator 6. Now I want to do that in sort of a clever way. You need to collect like terms, meaning if I scan through the numerator I see that there are x squared terms, x terms, and constant terms. I need to collect the coefficients for those terms, and I want to do it without writing everything out. So as I scan through I see, okay, I've got a x squared, bx, and x. All of those terms give me coefficients of x squareds. So if I look here, I get the a, and here I get the b. Those are the coefficients of x squared. Similarly, if I scan through and look for the coefficients of x, there's none out of this first term, and here I get cx, and here I get minus 2b. So c minus 2b x, and then the constant terms that are left are a from the first term and minus 2c from the last term. So a minus 2c. So this represents the numerator for this particular problem, and so this creates a system of equations. The system of equations is the following. The coefficient of x squared is a plus b. There is no x squared over here on the left-hand side. Because of that, that coefficient must be 0. In other words, I'm thinking of this 6 as being 0x squared plus 0x plus 6. That's how I'm thinking of the numerator. So the coefficient a plus b must be equal to 0. Similarly, the coefficient of x must be 0. And then finally, the coefficient of the constant term, or the constant term itself, a minus 2c, must be 6. Now, this is a system of 3 equations with 3 unknowns. You've probably solved this countlessly many times in your Algebra 2 courses in high school. Most people that write this will try to write it as a matrix. And so let me just show you the matrix form here. If you write it as a matrix, it would look like the following. We start off by considering the coefficients of A. A are 1, 0, and 1, so this is the A column. The coefficients of B are 1, negative 2, and 0. So 1, negative 2, and there's not 1 here in the third equation, so its coefficient is 0. And then the coefficients of C are 0, 1, and negative 2. And then finally, the constant terms, or the constant vector here, is 0, 0, and 6. Now, this is of the form that if you're familiar with matrices from high school, this is of the form A, where A is your matrix. Sorry, I don't need the vector notation there. A is your matrix, and then this over here is your vector. And one of the things that you learn is that if you row reduce this matrix, you can turn it into the identity matrix on this side, and then your answers pop up here. Now, this is a simple enough problem that I don't need to use matrices for it, but as these problems get bigger and bigger and bigger, matrices are really the only way to resolve the system of equations that's created. So if you need to go back and review a little bit of matrices, that might help you here. If you want to learn more about matrices, we offer a course called Linear Algebra that would definitely be a good time investment. So if I take my equations that I have, there's a couple of things I can do. I can use sort of an elimination method here to go about getting them. Let me just take a good example of this. I'll just take the first and the last here. So if I take the first equation, if I just take the first equation, a plus b equal to 0, and pair it up with the last equation, a minus 2c equals 6, then I can, just by subtracting these two, immediately come up with a new equation where a is now eliminated, and that's b plus 2c. So I'm subtracting these two. B plus 2c equals negative 6. Now, what can I do with that? Well, I compare this b plus 2c equals negative 6. I compare that up with the other one that I know, and that's minus 2b plus c. So I can easily pair those two up. Now, depending on which one I want to cancel here, I could do a lot of things. Let's go ahead and cancel the b. So I'm going to multiply by 2 on both sides or multiply by 2 on the top, and add it to the bottom. And that will cancel the b, and that will give me let's see here, 4c, so 5c, and then the top becomes negative 12. So we've been able to crack our first coefficient here. C is negative 12/5. Now, once I have that, I can immediately put it back into one of these two equations and use it to solve. Let me go ahead and do that. For example, right here, I know b plus 2c is negative 6. So if I have b plus 2c is negative 12/5, if that's equal to negative 6, then just doing a little bit of algebra here. Solve for b. Get a common denominator here. That's going to give us b is negative 6/5. And then finally, from this first equation, we know that a plus b is 0, so if b is negative 6/5, that means a is positive 6/5. So here are our three coefficients a, b, and c, which says that in terms of our integral, we can do the decomposition as follows. I can take, so let me clear a little bit of this out first. So let me go in and write what our coefficients are so we don't lose them. So a is 6/5, b is negative 6/5, c is negative 12/5. Alright, so now that we have those stored on here somewhere, let me go ahead and erase a little bit of this so we have a little more room to work. So I'll get rid of some of that scratch work there. And then let's go in and go back to the original integral. I can take our original integral, which is 6 over x minus 2 x squared plus 1 dx, and I can write it as the integral of a is 6/5, so this would be, there's a couple of ways I could do this. Let's just keep it all in the denominator. So 6/5 x minus 2 plus, and then over here I have minus 6/5 x minus 12/5. So that's what b and c are. And all that's over x squared plus 1 dx. Now that's not very pleasant to look at. I'm going to I'm going to distribute the integral through and make this look a little bit better by pulling out some factors here. And so this first one I can write as this, which we should immediately recognize how to do that integration step. This next one, I'm going to pull out a negative 6/5 from both terms. And so if I do that, I get the integral of, and then on top would be x plus 2 over x squared plus 1. So just recopy the first term here. And then there's one more step to do on the last integral. If I take this and break it up into two pieces, then the first piece I can break it up into is just the x over x squared plus 1. And then I can break it again over the 2. Does everybody see how that works? So I can break this up over each piece. Now I have things that I recognize how I might go about integrating them. Let's start off first with this one. It's the easiest one. It would be 6/5 natural log of x minus 2. And then this next one is minus 6/5. But I have to be careful here. I could use a u substitution. That would help me out a great deal here. If I let u be x squared plus 1, then du is 2x dx. And so in doing the u substitution, I'm going to end up with a factor of 1/2 that comes out of this. And so it's not actually going to be just 6/5. It's going to be 1/2 then. And then this will be, once you make the substitutions, 1 over u. And so being 1 over u, this is just natural log of u, but u is x squared plus 1. So if you didn't follow that, you might want to go back and look at your u substitutions, but this is a u substitution integral here. This one is, however, the third one here is not a u substitution integral. It's minus 12/5, taking the 2 out. That leaves you with x squared plus 1 on the bottom. Now that's one of these that you should remember. This is the arctangent integral. So 1 over x squared plus 1, the integral of that is arctangent. So since it's a definite integral, we need to add on our plus c at the end. But apart from, multiplying these two to get a simpler form, this is in fact the answer to our problem. Now this is a pretty involved example. We went through a lot of things, but this is typically how the book teaches it. You do need to be somewhat familiar with solving systems of equations, and it doesn't hurt to know some of your basic integration facts because they can get kind of complicated, even though you are making it much more simple, much simpler than the original integral that you started with. And that's the whole goal of partial fractions. Alright, thank you for watching.